We're going to continue with example 2 that we did yesterday. Example 2, we were looking at the function x squared defined on the interval 0 to L. First thing we did was we expanded that in a cosine series, then we expanded it in a sine series. What we left off on was half-range expansions. So all the Fourier series we had done before were defined between negative p and p. So we talked about what do we do if we're defined between 0 and L. And we said, well, we're going to need some definition of f of x between negative L and 0. So we said we could consider the function to be odd, we can consider the function to be even, or we could just consider the function to be repeating. So for the cosine series, geometrically, this is what we're looking at. From 0 to L, our function is x squared. So it looks something like that. Okay, if we want to consider this to be a cosine series, it's going to look something like that. So this would be our arbitrary definition of f of x between negative L and 0. So symmetric about the y-axis. If we are considering the function to be a sine function, or if that's the way that we are defining it, again, still defined between 0 and L. This time, though, we want the function to be odd, so we are going to reflect it over the origin. So this, then, would be our arbitrary definition from negative L to 0. So this is what we did yesterday. What we are going to consider today is what happens if we want this to be just a plain old Fourier series, not a cosine or a sine series. So this is the one that is going to be most different when you compare these two. That's our original definition. If we want this to be a Fourier series, we're just going to consider that to be periodic with a period of L. So from negative L to 0, it's going to look exactly the same. So the reason I say that a Fourier series is going to be more different from a cosine and a sine series is because what the period is. What is the period for A and B? 2L. Right? Period here is 2L. Right? Every 2L it's going to start repeating. What is the period here? L. Okay. So here we say that the periodic extension is 2L. Here we say that the periodic extension is L. Okay, for a Fourier series, all the formulas are in terms of P. So the first thing I want us to do is I want us to identify what P is. In A and B, P was L. Because we said we're defined from negative L to L. So hence P is going to be L then. What is P going to be for the Fourier series? L over 2. Right? Because if I go from negative L over 2 to positive L over 2, I still get the entire figure. It just looks a little bit different. Okay. So now we got to do the Fourier series, this time using a P of L over 2 instead of P being L. So A sub 0 is going to be 1 over P, so 1 over L over 2, integral from 0 to L of x squared dx. If you trust me, I will tell you that this is 2/3 L squared. So normally it would be negative p to p. In this case, we're starting and ending at 0 and L. If we want a of n, again, 1 over p. If I do 1 over L over 2, it'll be 2 over L. Integrating from 0 to L, x squared cosine of n pi over p x dx. Yes.
When you do a sub why
It's
is
like
the
the
limit
same.
0 to L if we said P was L over 2?
Because when you're doing just a plain old Fourier series, you go from negative P to P. So not considering the function to be even or odd. Just what we did at the very beginning.
What if we do that negative L over 2 to L over 2?
We're interested in, though, where it was initially defined,
Oh, okay.
which is 0 to L.
And so then what is that? When will the... Oh, that's...
So like a new center is...
So then it's really not negative P,
So then
it's just...
It's basically the same thing, because you're just multiplying by 2 like you want.
Yes. You guys are throwing me off. All these questions. Okay, yeah, you guys are forgetting the regular formulas. This is what I'm trying to say. So we're going back to the previous notes that we did. These formulas, this is the definition of just a plain old regular Fourier series.
Yeah, but if we said it was negative P to P, then it would be negative L over 2 to L over 2.
Right, I get what you're going to end up with the same.
But yeah, I understand that. But like that's what...
You're not the only person I'm addressing. I'm addressing everyone. Yes, you can also do that. It'll just be easier to work with 0. So that's why I'm choosing 0. Okay, are we all on the same page now? Okay, that's not convincing at all, but I'm just going to keep going unless you have any questions. Okay, so this is going to be 2 over L, integral from 0 to L of x squared cosine of 2n pi over L x dx. Okay. We're going to have to do tabular, obviously. So this is going to be cosine of 2n pi over Lx. If I integrate that, I'm going to have L over 2n pi sine of 2n pi over Lx. And negative L over 2n pi squared cosine of 2n pi over Lx. I think I'm going to have to go one more time. So negative L over 2n pi cubed sine of 2n pi over Lx. So this will be x squared, 2x, 2, and 0. Okay, so here we're going to add, here we'll subtract, here we'll add again. So we end up with 2 over L times the entire quantity, x squared L over 2n pi sine of 2n pi over Lx plus 2x L over 2n pi squared cosine of 2n pi over Lx. Subtract 2 L over 2n pi cubed sine 2n pi over Lx. Bless you. All of that being evaluated from 0 to L. So again, you could have evaluated from negative L over 2 to positive L over 2. As you can see now, algebraically, that would be more work. Okay. Plugging in L. We get L cubed over 2n pi sine. Once I plug in L, I'll be left with sine of 2n pi plus, this will be 2L cubed over 4n squared pi squared cosine of 2n pi minus 2L over 2n pi cubed sine 2n pi. Plugging in the 0, because of this x, that'll be a 0. Because of that x, that'll be a 0. Because of sine, sine of 0 is 0. So all of those end up dropping out. sine of 2n pi, that's going to be 0. That sine of 2n pi, that's going to be 0. So we end up with 2 over L times the quantity 2L cubed over 4n squared pi squared cosine of 2n pi. Can I simplify that cosine of 2n pi at all? Yes, how?
Simplify to 1.
Yeah, just 1, right? Cosine of any even pi is just going to be 1. So those 2's are a 4, we're going to cancel out with that 4. So ultimately we end up with a of n is L squared over n squared pi squared. Okay, b of n, 1 over p, so 1 over L over 2, integrating from 0 to L, x squared, sine of n pi over p, x dx. So again, this becomes 2 over L, the integral is 0 to L of x squared, sine 2n pi over L x dx. Okay, we're going to have to do tabular again. You tell me, is it helpful for us to go through the tabular again now, or we don't want to go through it together? Almost exactly the same as what we just did with sine instead of cosine. Okay, so can I just tell you what it ends up being? Ends up being negative L squared over n pi. So our general then Fourier series here, it's going to be a0 over 2, so that 2/3 L squared divided by 2, which gives us L squared over 3. Plus, here between a of n and b of n, we're going to take out anything that doesn't have an n, that doesn't rely on n. So I'm going to pull out L squared over pi. We're going to be left with the sum from n equals 1 to infinity. Here I still have that 1 over n squared and a pi, so I have 1 over n squared pi cosine of 2n pi over Lx. Here I'm still left with an n, so subtract 1 over n sine of 2n pi over Lx. Any questions on the half-range expansions, sine or cosine series? Okay. Zach asked yesterday